All right, this video is going to wrap up our kinetics chapter by talking about the reaction mechanisms for catalyzed reactions and how they are going to differ from an intermediate. All right, so a catalyst will increase the rate of the reaction without being consumed. And what it does is it lowers the activation energy. Okay, so it's going to lower it and allow for more reactions to be successful. All right, so in our example for this time, we have the decomposition of hydrogen peroxide. So iodine helps break that down. So you would put your iodine source, your iodide ion, whether it's Na, I, or Ki, right there. And this is broken down into two different steps, okay, elementary step 1 and step 2. So we have H2O2 plus iodide, and then we're going to make some water and some hypoiodide. This is going to be our slow step, which we know is our rate determining step. And then later on, the hypoiodide ion is going to react with some more H2O2, and it is going to make H2O plus O2, and then it will release the iodide solution. Okay, so when we add up all of our reactants and put them all over here, and all of our products and put them over here, we see that obviously things are going to cancel out. And we're going to see that our, oops, there should be a plus there, that the iodide ion is going to cancel out. That is going to be consumed in one part and then regenerated. So that's going to be our catalyst. And then our IO minus or hypoiodide is going to be our intermediate. It's going to be produced over here and then consumed. So it's this temporary species that occurs. And then we have our two H2O2s making our two waters and our iodine and our oxygen. So we get our overall reaction to occur. All right, so let's do our definitions. Okay, a catalyst is consumed in one step, but then it is produced in another step. So your iodide ion is going to be our catalyst here, whereas the intermediate would be produced or created in one of the steps, but then would be consumed on the other side. So our intermediate would be our hypoiodide, and we know the O means one oxygen and the prefix hypo. So you see that you still get the same overall reaction, but a catalyst and an intermediate are two different things. Okay, your catalyst gets consumed and then produced, your intermediate gets produced and then consumed. All right, so this guy goes this way, and your iodide would be left over afterwards. So I would then have iodide as my catalyst on the side. So if we look at these, we can obviously see that we have a slow step for our elementary step and a fast step. So again, what does the catalyst do? The catalyzed pathway is going to lower the activation energy. So this is going to be the EA of the slow step, and this is going to be the EA of the fast step. Notice the fast one is going to have less energy than our slow step, and obviously is going to have less energy than the uncatalyzed pathway that we originally talked about. Okay, so overall, we end up seeing that this is going to have an intermediate and a catalyst, and most importantly, this slow step is going to dictate that rate determining step. Okay, you can see the molecularity of the reaction, which means the molecules that are involved in the reactants, in order to figure out what it's going to be. So we obviously know that the rate is equal to the rate law constant times the concentration of our reactants, which is H2O2. It is first order here, and iodide in first order. So overall, this is a second order reaction overall. And it is very dependent on a catalyst. Okay, it will happen on its own without a catalyst, but it's gonna take forever. So we have to make sure that we know the difference between our intermediates and our catalysts, and we cancel them. Whoops, we cancel them all out so that we get our overall reaction. And that is our catalyzed pathway.